Hi everybody. I thought that since I wasn't going to be there to go over the answers to the practice test, that I would post a video of me going through the answers one by one. Hopefully that helps answer your questions. Number 1, the Earth is attracted to the Sun. Why doesn't it fall into the Sun? Well, same reason the Moon doesn't fall into the Earth. Same reason satellites don't come crashing down. It's because even though they are falling towards each other, they're moving so fast tangentially that they never actually land. Number 2, the gravitational force between two masses. So we're talking about the equation at the top of the screen here, your universal law of gravitation, G m over r squared. This force depends on how large the masses are. True. If the masses are bigger, that force of attraction is bigger. Choice B is always attractive. Also true. Everything in the universe with mass is attracting everything else in the universe with mass. Choice C decreases as the masses become further apart. Yep. The bigger R gets, the smaller F becomes. So our answer overall is D. All of the above. Number 3, if the mass of the Earth were increased but no change in its radius, your weight, aka force of gravity, would do what? Well, if we increase the mass of the Earth, one of the m's, that's also going to increase Fg. They are directly related. Therefore, your weight increases. Your mass does not. Number 4, suppose the gravitational force between two objects is 10 newtons. If the distance between the masses doubles, what is the new force? So this is a proportional problem. So we've got Fg equals G, m over r squared. Fg starts out as 10, but now we're doubling the distance between the forces, so r is now a 2 squared. Nothing changes in the numerator. So that means our relationship is a 1/4. So 1/4 of 10 is 2.5 newtons. Number 5, suppose the gravitational force is 10 newtons. This time both masses are doubled, so 2 times 2. And the distance between them doubles, 2 squared, so you get 4 over 4, which is 1. So the ratio stays the same, 10 newtons. Number 6, a rock and pebble fall at the same rate on Earth because, well, if you look at a rock versus a pebble, so this will be our rock, this will be our pebble. Force of gravity on the pebble is small, force of gravity on the rock is bigger. We know that to get force of gravity on Earth, you simply multiply mass times 9.8 if you're close to the surface of the Earth. If you look at that, 9.8 times the mass. The question wants to know, why do they fall at the same rate? Well, if you take the force of gravity, which is also the weight, and divide it by the mass, so Fg over mass, that ratio for all objects on Earth is 9.8. Number 7, a 40-kilogram woman stands at the top of a very tall ladder, so she's 1 Earth radius above the Earth. What is her approximate weight? So, when she was on the surface of the Earth, her mass is 40, so 40 times approximately 10 would be about 400 newtons. When she was 1 Earth radius from the center of the Earth. Sorry, this drawing is small, let's make it bigger. Center of the Earth. Here's her standing out here, being 400 newtons. If she is standing on this really tall ladder that puts her out another radius from the Earth, so this is just r, and we're doubling r, what happens to your force of gravity? Well, not changing anything in the force of gravity numerator. However, we are doubling the radius, and that r is squared, so you get 1/4 the force of gravity, so 1/4 of 400 is 100 newtons. Number 8, try to zoom in a little bit here. An object of mass m is on a horizontal rotating platform. It's 0.22 meters from the axle and rotates 1 revolution every 0.4 seconds. Since it goes around once every 0.74 seconds, this is our period. And we know that the friction is 13 newtons. What is the mass? So a quick force diagram for this little block at the current position it's at. You've got your force normal up, your force of gravity down, and the force pointed towards the center of this platform is friction, keeping it from sliding away. So in our case here, force of friction is our centripetal force. And we know that number for friction is 13. So that's going to equal mv squared over r. We can use our period to find the velocity, 2 pi r over t. Using the numbers in the problem, 2 pi 0.22 divided by our period of 0.74 gives us a velocity of 1.87 meters per second. And if we use that as our velocity and 0.22 as our radius, we get a mass of 0.82 kilograms. Number 9, which graph represents a relationship between the magnitude of the acceleration and speed of an object moving in a circle with constant radius? So we already know that centripetal acceleration is v squared over r. So the relationship between A and V is a direct square. Direct square relationship, second choice. Number 10, a ball of mass m at the end of a string is swung in a horizontal circular path of radius r at a constant speed, v. What combination of changes would require the greatest increase in centripetal force? So as you're swinging this thing around, first of all, tension is your centripetal force. And so the question is basically asking which changes would make the tension in the string the most. So in none of these are we changing m, so m is not factored in. So we want, in order to change tension the most, we want to change the numerator, make it a lot bigger, and make the denominator a lot smaller. So for example, choice A, if we double the velocity, you get a 2 squared on the top, and you double the radius, there's a 2 on the bottom, you get 4 over 2, so that's doubling the tension. In choice B, if you double velocity, 2 squared, and you cut the radius in half, now you got 4 over 1/2, which is 8 times the tension. Choice C, if you half the velocity and you have the radius, you got 1/2 squared over 1/2, so that's 1/4 divided by 1/2, that gives you 1/2. And if you, for choice D, half the V, so 1/2 squared, and double the radius, now you got 1/4 divided by 2, which is 1/8. So which of these options increases this tension the most? Choice B. Number 11, an object moves at a constant speed in a circular path. Which vector represents a centripetal acceleration? That is always pointed towards the center of the circle. That is choice 3. Number 12, a 0.055 kilogram puck is attached to a 0.15 kilogram mass m by a cord that passes through a hole in a frictionless table. The puck travels in a circular path of radius 0.25. What's the speed of the puck? So this is very, very, very similar to the problem that we had in a collected homework assignment where you were swinging the rubber stopper around and then there was a hanging mass below. And if you remember in that problem, if you drew a diagram for the puck, here's our puck, here's our string, it's going down through the table and there's a hanging mass down here. Sure, you've got a normal force and a force of tension, or force of gravity, but there's also this force of tension towards the center of this big circle that you're making on the table. That tension is your centripetal force, and what is causing that? It's this hanging mass down below. So it works out to this force of tension is your force centripetal, and this force tension is big mass m times 9.8 and that equals little mass, m, the little puck, times v squared over r. And at this point you just plug and chug. If you do so, you get a velocity of 2.58 meters per second. Choice D. 13. A student plots a graph of centripetal force versus v squared. What's the slope? So we know centripetal force is mv squared over r. Think about this in terms of y equals mx plus b. Our y-axis is fc. Our x-axis is v squared. The slope is whatever's in front of x. Whatever's in front of x here, m over r.